Okay, people, welcome back to another discussion, or maybe the final discussion of Chapter 4, although I do have a lot of material. I'm not sure if I'm going to be able to get through it all. However, let's see how far we can get. Okay, so last time we finished up um, talking about this Gibbs-Helmholtz equation, and there's actually another way to write this out. Okay, so we can also, and I'm just going to call this the GH. We can also write it out in a different way, and they give a bit of information about how to actually derive this in a book, although not that much. And if you're interested, you can probably figure it out. But there's a different way to write this. That is especially useful. Okay, so we can also write this as the partial with respect to delta G over T over the partial of 1 over T at constant pressure is equal to delta H. Okay. Now you might be looking at this and thinking to yourself, my goodness, this is so complicated, I can't even figure out what it's trying to say, let alone figure out why it's especially useful. But it turns out that it is especially... Wow, this is really bad. I'm just going to write it out. Okay, it turns out that it is especially useful if we think about this in terms of graphs. Okay, let's think about this. Let's put on our graphing helmets. Graphing. Let's put on our graphing helmets. Whoa, really bad graph. Sorry. And think about what this actually means. Okay, so we're looking at the change in delta G over T versus the change in 1 over T. Okay, if we plot delta G over T versus 1 over T, and we actually do some measurements, maybe at several different temperature points, looks something like this. Okay, we can start to figure out what exactly is going to happen here. If I then fit this with a straight line, the slope that I pull out here is equal to delta H. So I can measure delta H by, or I can infer delta H by measuring delta G and temperature at the same time, okay, by making one of these graphs. So this is an especially useful form, especially when thinking about different types of experiments that can be done to relate delta H to delta G. Okay, so we have figured out that the Gibbs-Helmholtz relationship is a relationship between G and T. Okay, so this is the relationship between the Gibbs energy and temperature. What about the relationship between G and P? Okay, what about G and P? How do they relate to each other? Well, if you recall from our natural variable relationships, d, or the partial with respect to G versus the partial with respect to P at constant temperature, is equal to the volume. Okay? And if we assume at this point, so we're just going to assume that this is an isothermal change. Okay? If we assume that, we can rewrite this as dg, so the infinitesimal change in G, is equal to volume times the infinitesimal change in P. Now, we can integrate this whole piece, or integrate both sides, and of course on this side, since G is a state function, we get delta G, and on this side we get the integral from Pi to Pf of V dP. Okay. So for the condensed phase, so basically liquid, solid, etc., we can assume that V is relatively constant with P. Okay, so if you change the pressure by a small amount, then V is relatively constant. So that means that delta G is equal to V dP, okay, which we end up seeing is just V times delta P. Okay, but that's for the condensed phase. What about the gas phase? Okay, if we assume for ideal gases, for ideal gases, we can write the volume as nRT over P. Okay, so that's how the volume varies with P. We can plug this guy back in up here, and we can solve. So then therefore delta G is equal to Pi Pf integral of nRT over P dP, which is equal to nRT Pi Pf of dP over P. Now the integral from Pi to Pf of 1 over P dP is the natural log. So this becomes delta G equal to nRT natural log of Pf over Pi. Okay. Now this is assuming an isothermal change. Okay. So only for isothermal is this equation relevant. So this is how delta G changes with pressure, G versus P. Okay, so now we have an expression for that, for both gases and condensed phase. Now I'm going to move into something a little bit different, okay? A little bit different. So let's actually start talking about some chemistry. If you've noticed, ooh, that's weird. If you've noticed, so far, we have been focused almost exclusively on physical changes. So, for example, changes in pressure, volume, temperature, etc. Okay, we have almost exclusively been focused on this, and as a matter of fact, we have been assuming that n is constant in all of this. So for all of these natural variable equations, all of the partial derivatives that we've written, really, even though we've been writing them as, for example, du dv at constant t, they should really be written as du dv at constant n and t. Okay, because we've been assuming that n is constant this whole time, so we haven't really talked about it too much. But the n is what's important for chemistry. So far, we've only talked about physical changes. Let's get back to talking about chemistry. Let's get back to talking about n in particular. And we are going to... Okay, so with respect to that, if we think back to all of the different things that we've done with P, V, T, etc., right? We've been taking partial derivatives with P, V, T with respect to these state functions. So can we do the same for n, or can we take the derivative or find derivatives of n? Or maybe we should say with respect to n. And of course, as you guessed, probably the answer is an emphatic yes. And this is what we will be doing from here on out, essentially. Okay. And one more point I want to make before we actually get into this. It's like the worst double arrow ever. Is that the majority of the derivatives that we're going to care about with respect to n are going to be in terms of the Gibbs energy. Okay, and this is for the sole reason that G, it turns out, is most useful for chemistry. You can define all of the terms that we're about to define here in a second in terms of all the other state functions, and honestly in terms of all the other state variables as well, but they're not as useful as defining them in terms of G from the perspective of figuring out the spontaneity of a chemical reaction. Okay, so for the most part, we're going to stick to G, and we're going to come up with some derivatives and looking at how N changes with respect to state functions and state variables. Now, the first one I'm going to talk about is something called the chemical potential. And you guys have experienced this in different classes. It's been shown to you in different ways. Today and in this class, we're going to come at it from a purely thermodynamic perspective. Okay, and the way that we're going to define the chemical potential, which is given the symbol mu, is the partial of G, or the change in G with respect to the change in N at constant temperature and pressure. Okay, so that's all the chemical potential is. It's just the change in the Gibbs energy with respect to the change in the number of moles. Okay? And importantly, mu is defined for each substance. Okay, so it's defined for each substance within a reaction. And actually a better way to write that then is to call this mu sub I, where I is the substance. Oh, you know what? I should be writing these. This is a definition, so these should be a triple equals. So we can write mu as the change in G with respect to the change in N sub I. Okay, so this is the substance of interest, where T, P, and N sub J, where J is not equal to I, are constant. Okay. In this case, only the ith substance is considered, and all other substances are constant. Okay, so it's only one substance at a time that's considered here. And you can imagine what this is going to do to the infinitesimal change in G. We can no longer just write that in terms of the change in T and the change in P. We now have to include the change in N. Okay? So this infinitesimal G, or dG, must now be written as dG is equal to the partial of G with respect to temperature at constant pressure and N's. I'm just going to write N, all of the N's, plus the change in G with respect to P at constant temperature, N's. Okay? Oops. Okay? Now we have to add on a new piece. Okay? To all of this, we have to add the sum over all i's, so over all of the substances, of the change in G with respect to the change in the ith molar substance with T, P, and N, J, J not equal to I, times D and I. Okay. So this is summing over all of the possible chemical potentials. And now the infinitesimal change in G includes the possibility for Ni to change. Okay, now a little bit easier way to write this, that's, I think, well, it's more compact, so it's easier to remember, is dG is equal to negative S dt plus v dp plus sum of mu I dni. Okay? And oftentimes this equation here is called the fundamental equation of chemical thermodynamics. Okay, this is the fundamental equation, and so you can kind of see that this is basically giving you all of the information that might be happening within a chemical reaction. You have temperature, you have pressure, you have delta G, you have the change in the number of moles. So all of this, everything contained in here gives us the information of, or the important information during a chemical reaction. Okay, and a few more remarks about mu sub I, or the chemical potential. Mu sub I is the first example in this course of a partial molar quantity. We'll be seeing more of these as we go through the book, but this is the first example of this. And the chemical potential, let's try to define this in more easy to understand terms. Let's try to describe it in words rather than just writing out the formula. The chemical potential is a measure of how much a species or substance or whatever, how much that substance wants to undergo a physical or chemical process. Or not process, change. Okay, and I'm putting wants here in quotation because, of course, the chemical or substance doesn't really want anything at all. We're just anthropomorphizing the molecule to make it a little bit easier for us to understand. Okay, so the chemical potential is a measure of how much a species wants to undergo a physical or chemical change. Okay? Another interesting bit of the chemical potential is that if we have a mixture, so if we have two or more substances, that exist in a system together, okay? And if these two or more substances have different chemical potentials, then what happens is some process must occur to equalize the chemical potential values. Okay? So if two more substances are in a container system, whatever, and they have different chemical potentials, then some process, whether it's chemical or physical, must occur in order for their chemical potential values to become equal. Now, this should start ringing some bells in your mind, okay? This should start ringing some bells in your mind. And actually, next chapter, we're going to deal almost exclusively with this. And when you start to see things like it will equalize and some process will occur, you should really start thinking in your head equilibria. Okay? And that's exactly where we're going next. We will start to define equilibrium or chemical equilibrium in reactions in terms of this idea here, where the chemical potential is equalizing. Okay, this is the driving process that's driving a chemical reaction forward, is this equalization of the chemical potential. Now, before we get into this idea of how chemical potential and how thermochemistry can be related to equilibria and chemical reactions in general, we need to define one term. It's not a term, it's an idea. We need to define something. And this is called fugacity. Okay, we need to define the fugacity. The fugacity, apart from being a really freaking awesome word, I just love the way it sounds. Fugacity, fugacity. It's a cool word. Apart from being a cool word, fugacity is a measure of non-ideality of real gases. Okay, it's a measure of non-ideality of real gases. Okay, and to get into exactly what it is in terms of derive it, I'm going to start from what we came up with before of delta G, or the change in G with respect to the change in the pressure. Remember, this was nRT times the natural log of the final pressure over the initial pressure. Okay, so in this case, we say that G varies with P. Okay, now I'm going to suggest that chemical potential also varies with P in a similar way. Okay, so I'm going to say that delta mu is equal to RT times the natural log of the final pressure over the initial pressure. So mu also varies with P in a very similar way. Okay? Now we can rewrite these two reactions to include the explicit G final minus G initial and mu final minus mu initial. So I'm going to call this Gi minus Gf is equal to nRT times the natural log of Pf over Pi. And mu I, same thing for mu, minus mu f is equal to RT natural log of Pf over Pi. Okay? Now, I'm going to assume, oops, I did this so backwards. Why didn't anybody say something? Gee whiz. You're just sitting there, writing down your notes, not telling me that I made a mistake. Gosh, you guys. I have this backwards. Okay, so the final minus an, oh my goodness. I can't do an I to save my life. Okay, so next what we're going to do is we are going to assume that the initial starting point for both G and mu is at some, so let's say initial point at some standard pressure. For example, 1 atmosphere, 1 bar, etc. Some standard pressure, doesn't matter what. And we're going to call these standard G's G standard and mu standard. Okay. Now, if I plug these guys back in up here, then solve for GF and mu F, and kind of get rid of the F and just say that this is at any pressure, or we can rewrite this as G is equal to G naught plus nRT ln of P over P naught. And we can rewrite the chemical potential as mu equals mu naught plus RT times the natural log of P over P naught. Okay. So we see from this that mu changes with the natural log of P essentially. Okay. So that's how mu changes. And if we look at that on a graph, it looks something like this. So we have E and P. It should look something like this. This is a natural log curve. So this is ln of P. Okay. And this is what happens in the ideal case. But in the real case, it doesn't look anything like this. It's kind of up and then down and then goes back this way. Okay. And this is the real case. So the real case, the real gas, as we know, doesn't act anything like an ideal gas. It's a fairly good assumption or a fairly good approximation to say that something is an ideal gas, but it is nowhere near being an actual ideal gas. Okay. And this curve, the real case, can be broken up into three distinct regions. Okay, so at very, very low pressure, the real case approaches the ideal. Okay. So at very low pressures, all gases behave like ideal gases. Okay, and this kind of makes sense. If you lower the pressure enough, you get to the point where there's zero interactions, which is the number one reason why gases are non-ideal. It's because they're interacting. And the ideal gas law is assuming that there's no interactions. Okay? So that's the first case. The second case is at intermediate or medium pressures, so somewhere in the middle. The real chemical potential is lower than expected. Okay, that's this region here. Okay, so the real chemical potential is lower than expected, and this is due to the fact that real molecules slightly attract each other. Okay. Real molecules are slightly attracted to each other, and this lowers the energy. It lowers the energy and therefore lowers the chemical potential. Okay? And then there's a third part of this graph at high P. And this is the region up here. Okay? At high P, the real chemical potential is higher than expected. Okay? It's higher than expected, and this is due to the fact that the molecules are so densely packed they start to repel each other and therefore increase the energy. Okay. So they're so dense, they're so close together that they start to repel, therefore increase the energy, and therefore increase the chemical potential. Okay, so that's how chemical potential changes with pressure. And as we see, there's some discrepancy between the actual ideal case and the actual case and the ideal case. Okay, so we need to begin to start treating real gases slightly differently. Okay? And this is where sorry, I lost my train of thought there. This is where the idea of something called fugacity comes in. fugacity is just lowercase f, and it's defined as being phi times the pressure. Okay? So fugacity is simply a scaled pressure. That's all it is. This phi here is the fugacity coefficient. Okay, so it's the fugacity coefficient, and this is the pressure. And the fugacity has units of pressure. So atmosphere, bar, whatever you use for pressure, that's the same unit that you have for the fugacity. And from now on, fugacity is the proper way to define pressure of a real gas. Okay, so it's the proper way to define that pressure. We can plug this back into our chemical potential equation. So mu is now equal to mu naught plus RT times the natural log of F over P naught. Okay. Now at at pressure equal to 0, remember on the graph everything kind of approaches this ideal case. So at pressure equal to 0, phi equals to 1. Okay, so all gases are ideal. So we can rewrite this as the limit as pressure approaches 0 of fugacity is equal to P, and the limit of pressure approaching 0 of phi is equal to 1. Okay. Let me check the time here. 30 minutes. Yeah, this next part is pretty intense. I think I'm gonna save this for next week because if I get into it, then we're gonna have to finish it today, and it's quite dense. Not next week, next time is what I'm saying. It's quite dense, but we only have a little bit left of chapter 4, but I think I will leave that until next time. So I'll make a note here. That's where we stopped. And yeah, we will pick up with that on Wednesday. Don't forget that we have homework due today. If you have any questions on it, please let me know. Otherwise, I hope you guys have a great day. And yeah, I hope you have a great time doing the homework. All right, take care.